As we begin talking about magnetic field, it's important to remember what we learned about magnetic force, that only a moving charge will experience a, the effects from a magnetic field, and we can look at either singular moving charges. We can look at a line of charge through a wire. A singular charge will move in a circular path because the force is always perpendicular to its motion, whereas a wire will actually get pushed one way or another because you have a line of charge over some length or over some distance. We have the first right-hand rule, which allows us to find the magnetic field around any current carrying wire. And we have the third right-hand rule, which is straight fingers, thumb straight out to the side. I call it the stop hand. And that is to find the magnetic force acting on a moving positive charge or a line of positive charge. Pardon me. If I have a negative charge, my answer direction is just the opposite direction. So here we're on slide number 26 from the notes, picking up where we left off. And this is looking at a magnetic field from an individual moving charge. Now we know directions and that sort of thing, but in figuring out how this works, and this gets a little bit sometimes tough to see because all of magnetism is three-dimensional. You always have three dimensions happening. So what I have here is I have a charge moving to the right. That is going to be my source. If it moves, it produces a magnetic field. If it's stationary, it does not. It's always producing an electric field, but a magnetic field only if it's moving. So if I take my right hand and literally do this right now, look at the screen, take your right hand and put your thumb to the right in the direction of V. That's the direction it's going to be moving. Just like if I had a line of charge in a wire, I'd have my thumb going to the right. Your fingertips are going to be pointing at your face when they are above my dotted line. And then you can see I've got green dots showing the magnetic field pointing to you. You don't have to necessarily rotate your hand this way, but if you kind of rotate your fingers forward a little bit, you can see that if your fingers continue to follow their curled path, they will eventually go into the screen down below. And so what I get is a series of circular magnetic fields in the vicinity around, I should say, this is the center of all of those little circles, this moving particle, just like if I had a wire. The difference is that we have a long wire. You expect to see a field around the wire everywhere. This one's a little bit more challenging to see because even though this particle hasn't reached this spot yet, there's still a magnetic field produced along the line of its travel. This magnetic field here and here makes perfect sense because it's right where our particle is. These magnetic fields here, they're not going to be as strong because the distance is farther away, but I still have a magnetic field produced here. I still have one back here. So we're not here anymore. We were here a few seconds ago, but now we're there. I still have a magnetic field back here. The farther away, R1 versus R2, the farther away we are, the weaker it is. So we have gravitational field, big G, big M over R squared. We have an electric field, K big Q over R squared, and we're going to get something similar, and having an R squared relationship should make perfect sense for this individual charge. So our list right here is everything that's going to affect the strength of that field. How much charge and how fast we're going. Up here, how far away we are. And we also have this cross product, right? This is going to be a big one. So the sign value, which is a cross product. So this is where it gets weird, and this is where we just have to make sure we practice. So if I come down here, what I see is my relationships, the four of them, all put together right here. Now, this is just a relationship. We need to have a constant. Big G, epsilon naught, 4 pi epsilon naught, etc. Our new constant is mu naught. So instead of epsilon naught, which was the permittivity of free space or a vacuum, we now have the permeability of free space. It sounds very similar. So mu naught over 4 pi. And conveniently, mu naught is 4 pi times 10 to the negative 7th. You can work it out with taking pi out of there, but this is what mu naught is. So when you go with mu naught divided by 4 pi, very, very convenient. All it is 10 to the negative 7th. So that means all you have to do is do your work, and at the end, you take out the mu naught 4 pi, and you just throw on a 10 to the negative 7th. Now, obviously, you're not going to be doing any testing for me, but obviously, for someone else in the future, you're going to want to make sure that you write out final answers in proper scientific notation. So you get like an answer of, 13, and you say, just throw on the 10 to the negative 7th. We all know that 13 times 10 to the negative 7th is not the proper way to express your value, so just keep that in mind. But again, you're not going to be taking a test for me, so you don't have to worry about it in this class. So this sine function is telling us about that cross product. Here's the problem. The cross product has to be between v and r, but they're not multiplied, they're divided. But I still need their orientation relative to each other. I still need it to be perpendicular. Let me show you what I mean if I go up here. If I add in r3 and I take an arrow and say, okay, what about a point right out front? Well, right out front, I have 0 perpendicularity to this particular location. It's right along my line here of motion. I'm going to get 0 magnetic field. So I need to have a location that is off of my line of travel. And as soon as I do that, I end up with some kind of a perpendicular component. So again, I need to have a cross product. And the issue is that the cross product has to be between v and r, but they're not on the same side of the division bar. But I still need that relationship. So what do? Is we add in r hat. So we remember I hat, we remember j hat, k hat. What do those represent? Unit vectors. Those represented a vector that had the length of the value 1, literally 1. So we could throw on an I hat or a j hat. So my answer is 5 times I hat. Well, the times 1 doesn't affect the value, and the I hat gave us a direction. So this right here is simply a 1 unit direction allowing me to do the cross product, since my actual r variable is down here. So this is just a directional variable. And this is going to be the magnetic field from a moving charge. Now, once you get used to r hat, it's not a big deal, but you do have to get used to it. So when I come down here, r hat is a direction that has the size or the length of 1. So we know how to do that. R vector, which is magnitude and direction, divided by just the magnitude. This gives me a ratio of 1, and I'm left with a direction. That direction can turn into an I hat, j hat, k hat kind of a thing. So these directions, it's from the source to the point in question, just like anything else we've been doing so far. Right? So your magnetic field direction, you can take that singular point that's moving and do the first right-hand rule like we did at the very beginning. And just pretend, visualize it like it's a line of charge, and that's very easy to do. Or you can do V crossed with R. Remember, cross product, you use straight fingers, straight thumb. Thumb cross fingers equals palm. So I'm going to do this one. I'm going to go up. Okay, so I'm going to look at R1. I've got my thumb is V. That's going straight across my board or my screen. My fingertips is going to be R, so I put my fingers down. And at point P1, I have a velocity to the right with my thumb. I've got an R1 down with my fingers, and my palm goes in. And right there, that green X is my palm going in. If I do the same thing for R2, I have going out in this direction, I need only the perpendicular component. So I can draw an arrow right, and then I draw my arrow down. The down arrow is the perpendicular arrow. And I have the same third right-hand rule. Thumb going to the right, fingertips going down, palm literally going into the page. So at P2, I get an X. And as I'm saying this to you, I'm literally doing the third right-hand rule. You should do the same. Now, when I bump to the next slide here, this right here is my way of trying to visualize or illustrate what the magnetic field looks like for this particle traveling to the right. I get the biggest amount of field here, and then it gets weaker and weaker and weaker in front of my particle. Now my particle will eventually get here, and as it gets to this location, this loop gets bigger and bolder to show that it's stronger, and this one gets a little bit weaker. But I get this weakening field back here, and fields over here weakening, but as I move, my distance to each of these changes. And as I get closer and closer and closer, the field gets stronger and stronger and stronger. So if we put this to use, I've got a particle moving this way. I've got R1 and I've got R2, two separate locations. So what I'm going to do is I'm going to start with location number 1 because that's the easiest. Perpendicular is always the easiest. I've got a charge. Notice there's a negative. A negative simply means my final answer is going to be in the opposite direction than what my math says. No problem there. I've got my velocity in the I-hat direction. Looks like R1 is going straight up to point P1, and this thing is at the origin. So I'm going to move over here to the right. And so what I see is my method for finding R-hat. It is the vector divided by the magnitude. So what is my R1 vector? It's 0.5 up, so it's 0.5 positive j-hat. If I divide out the length, it's 0.5, and my R-hat is positive j-hat. So my unit vector is another unit vector. And when that happens, it's because we have nice perpendicular things, and it's very simple. So I come down here, I plug in my values. I know this is 10 to the negative 7th. Math, math, and math. That's easy enough. But I do have this cross product. This is only going to give me a direction. I cross j equals positive k. You can do that with your thumb. Thumb cross fingers equals palm, so I cross j. My palm comes out positive. So, didn't mean to do that. So, I've got my 3 numbers. I've got my 13. I chose the number 13 in my diagram earlier, completely random by the way. 13, 10 to the negative 7th, and a positive k-hat. But we said we had a negative source, so I throw a negative sign on in front. Don't forget the unit for your magnetic field is the Tesla. That's the easy part when you have a location that is perpendicular to your velocity. What happens if we don't have it perpendicular? Here's R2. I'm doing the same thing I did before, it just looks a little bit more confusing. So my R vector is going to be 0.5 in the I direction, 0.5 in the J direction. So I'm going to express it with my unit vectors I and J. I'm going to divide that by the total length. Well, the total length is Pythagorean theorem, right? So it's a squared and b squared equals c squared, so that's it right there. So you take a look and I simplify that a little bit. I divide through and I get my R hat looking like this. You say, oh my gosh, this looks so much more challenging. Well, it's not too bad because what happens when you go I crossed with I? I crossed with I is 0, right? So I come down here. So I'm not sure why last year, I'm not sure why I didn't put in a little cross product right here. There should be a cross product. I'll see if I can squeeze one in. I'll even go with blue on the spot here. So there should be a little cross product. Better than nothing, I suppose. So I've got my cross product there. So when I go I cross I, that's just 0. So what am I doing? I'm doing the same thing I did over here. I'm just doing a cross product with a 0.71 instead of a 1. And if we think about that, it makes sense. We're a little bit farther away, and I have this as my perpendicular component. So I come down here and I just run the numbers through. So I end up with my negative because it's a negative charge. I got my Tesla, I've got my k hat. And notice the direction is the same here, negative k hat and negative k hat. And we can double check this. Okay? So literally, right hand, your thumb is going to the right, which means R1 and R2 are located where your fingertips are coming out towards your face. That's out, positive k hat. That's what a positive would do. A negative would produce the opposite, which means into, negative k hat, which is exactly what we calculated down here. So what happens if I have a segment of current carrying wire? I'm going to use the same equation that we just did. That equation is going to be mu naught over 4 pi. I've got charge times my velocity crossed with r hat divided by r squared. Same equation here. I'm going to look, though, at one teeny tiny small little segment. So I'm looking at one teeny tiny small little segment. I'm going to find the teeny tiny little amount of magnetic field from that small segment. So here, our current is going through this wire. The wire has a cross-sectional area A. That's the width or the thickness of the wire. I've got current going this way, which could be thought of as a positive particle literally moving this way. So VD, our drift speed. The total length is L. DL is going to be the small little length. Now I already know what the direction of my magnetic field should be. I can see these green arrows. Everybody take your right thumb, jam it in towards the screen in the direction of your current. Your fingertips are pointing to the right. When I look at the location above my wire, your fingertips are pointing to the right. And I know that it makes a circle around the wire. And so that means I have these green lines are tangent to the circular shape that I have as I go around the wire. Now I get to right here. I get my DQ, my VD. Now I have my red vector arrow. And instead of worrying about a cross product and an r hat vector, I just need to find the r and v components. So all I need is the component of r that is perpendicular, and that's going to be this right here. So if I go with the sine function, that will take care of v cross r hat using the sine function. So I can plug in sine, and I'm ready to go, but I'm not really sure where to go from here. So if I scroll down, we did this long ago during our current section. Capital N was our particle volume, the number of particles in a volume of wire. So the number, I can use algebra and rearrange how many particles I have is going to be this ratio multiplied by the volume, which is the area multiplied by the length. So to figure out the amount of charge, all I have to do is take the number of particles here and multiply that by the charge of each individual particle, which is our elementary charge. So I get ENAL, and if we look at really, really small portions over small lengths, no problem there, and as soon as I divide it by time, I now get current. Length divided by time is my speed, our Nevada equation, if you remember that one. So using that, I slide back up. dq can be expressed as ENAL. So this right here is my dq. It's the particle density, it's the volume, it's the charge of each one. V is the speed of my particle. And I see those four variables. That's current. So I can replace that with current. So I get I dl over r squared. I have the sine function here. Remember, that is just telling me that I need perpendicularity, cross product. And so I put the cross product back in. And this right here is known as the law of Biot-Savart. It's a French name. I don't speak French very well, which is why when I say it, Biot-Savart, it doesn't sound cool. If someone knows how to speak French and they say it correctly, it sounds really awesome. So this is the magnetic field caused by a wire segment. And the reason we write it out like this is because you can have a wire that has different bends and different directions very, very easily. So you technically are going to look at just small little segments. If you have a long segment that's all following the same thing, then obviously this turns into L and B. So putting this new thing to use, here's an example. We'll show you how to set it up, and then we'll kind of move forward. You don't need to see me read through lines of algebra. But I have here is the location in question, point P, some distance away, x. And so what I'm going to do is I'm going to look at small little segments of length, and since it's a vertical, I'm going to use dy, and I can measure the location of dy with my blue y. We're going to keep this simple and go right dead center of this little segment of wire. So I've got positive A up top, negative A down low, and I can see what the distance is going to be here. So law of Biot-Savart looks like this. So my cross product, I can just go with the sine function. So I've taken care of that. My current is a constant, so I bring current out front. Very common to do that. And so I'm left with the small length of wire, dy, the sine function to take care of my cross product, and then my distance away is going to be my, using Pythagorean theorem over here. Anytime we have a non-circular issue, or a non-circular question, I should say, that we don't have a semicircle or a circle, it's pretty common for us to take the sine function and express it as a ratio instead, because we don't have a very convenient angle to kind of trace through. So sine will be the opposite side, which is a constant x, divided by the hypotenuse, which will vary with y. Right, so now I can put those in, and so this right here is where I start to do my integration. So now I integrate. Notice x has been pulled out, it's a constant, so all my constants are here, and then there's this. And this is where you're going to apply your calculus knowledge. What we're going to find is that using a trig substitution, which we've done in the past, is going to be the way to go. And once you get used to trig substitutions, they're not terrible. It looks like there's a lot of lines here. I just went through when I did this one, I was going line by line so that everything made perfect sense. And we get to the bottom, and we end up with this right here as our final answer. Now what happens as the length of our wire approaches infinite distance, infinite length I should say. And either that means that we're really, really close to a small section of wire, or the wire itself is really, really long. Well, as soon as we do that, A kind of sees itself out, because I get basically x squared is irrelevant, so I get infinity divided by infinity, so I just get a factor of 1, and I end up with mu naught I over 2 pi x. If you looked in your textbook, they would replace the letter x with the letter r, because x kind of implies a horizontal distance. And this right here is a very common equation. This is for the magnetic field around a current carrying wire. Notice you don't have an r squared down below like you do for an individual particle. Individual particle, you have this field, right, coming from a single particle. Well, here you've got a line of charge. You've got particle after particle after particle, all producing these magnetic field lines. And so what you find is that the magnetic field drops off at a slower rate because you have more particles producing that field. So continuing on with more examples, so here we have a loop. It's in the YZ plane. Z is going into the board, and Y is going up and down, obviously, and X is going straight to the side. So basically you're looking at the side view of this loop. And if I kind of scroll down, that's what we're looking at right there. So my Y is here, my Z is straight into the board, and then here is my X. So that's what we're looking at. So what I can see here is that my current is going around in a circle because it's a complete loop. These two currents are going to cancel each other out in terms of any magnetic field, so I don't have to worry about those. So I get this current carrying loop. I've called it radius A. I like R for particular things, so R is my go-to, so I'm not going to call it radius R. So radius A, so there is radius A, distance away X, so my current coming out, so you can quite literally do your first right hand rule. Thumb comes out towards your face right here, and at this location, I see that I'm, well, around the whole thing I should say, I have a counterclockwise direction. So counterclockwise means right here, tangential is going like this. Here, thumb in clockwise. So my red arrow is doing that. So what I see is the symmetry canceling out my vertical. And not just my vertical, but if I were to look at two locations, so instead of looking at a location up high and down low, if I look at, I didn't mean to move that. If I take a look at this location and this location, I'm going to have cancellation in the Z direction as well. So my YZ plane gets completely canceled out, and so all I have right there, YZ plane cancels out, so all I have is my X direction. So just like before, looking for symmetry is always very beneficial. So we come up here, law of Biot-Savart, there it is, cross product. Well, DL is some tiny little segment. Point P is way out here, so to get from here out, I'm going tangent to the loop, and that loop has my current carrying wire, so they're perpendicular. So just like that, cross R hat is done. We are going to use cosine because we've already decided that we only need the horizontal component, hence the cosine. So I come up here, and so what do I have? I've got my I brought to the front. I've got my DL, my R squared. Well, R squared is going to be right there. So there's my distance squared, so I end up with A squared plus X squared equals my R squared, so I end up with just A squared plus X squared, the cosine to get only the X component. Now, since we're dealing with a point on the axis here, what we're going to find is the angle that is made with, for our magnetic field versus our dotted line, it's going to be a constant. So this cosine theta, it's a constant made out of constant numbers, so throw it in as a ratio. And everything is a constant except DL. So this is one of those very easy integrations. DL is going to be the length, which is circumference, 2 pi r. In this case, the radius is listed as A. And so as I continue to scroll down slowly, just doing the math, and we get to our final right here where this represents the X direction. Now, what happens if we look at the dead center? Dead center, it means X goes away, and we end up with mu naught I over 2A. Every coil I have will double, triple, quadruple the amount of field I have. So if I have 5 coils, I take this value, multiply it by 5, and so I can throw on the letter N there. So that's going to be the magnetic field at the center of a loop. So this right here is just a mathematical sample of finding the magnetic field at point P from 2 separate charges. They are both going to be in the Z direction. Whether it's positive or negative k hat depends on their charge and their direction. So you're just going to find 2 values and you're going to combine them as vectors. So it looks like I get 2 negatives, so they're both pointing in the negative k hat direction. So combining them is easy. So you can kind of go through that one and check your work if you'd like. Now when it comes to flux, we talked about Gauss's law and how flux is not going to be very useful when it comes to a magnetic field because all of our magnetic field lines are continuous loops. They always make a complete path, which means that if I try to enclose right here, this little symbol, right, a closed surface around some charge, some magnetic source, however many lines, how many arrows I should say, that represent magnetic field, the number of magnetic field arrows coming out, is going to have to equal the same number coming in because it's a complete closed loop. So it's all 0. So that right there is Gauss's law for magnets. There's some usefulness at the end of all of this as it relates to how light functions, but for us right now, doesn't matter. It means we don't have to worry about it. So instead what we have is the idea, well, let's not do an integration over a closed surface. Let's do an integration over a closed path. So it's still a closed path. We still start and stop our integration at the same point. We're going to do a length instead of an area. This right here, another French name, ampere. This is Ampere's law, and this is going to basically be the magnetic version of Gauss's law. Technically, this is Gauss's law up here. We can't do anything with it, but the way we use it, the way we use Gauss's law for electricity, we're doing the same thing here for magnetism. We're using a line instead of a surface. So you get to decide what the line looks like, just like you got to decide what the surface looked like. You're going to want one that has a constant magnetic field along the line. You're going to want one, since we're doing an integration, having a constant is nice. You're going to want the magnetic field to be either parallel or perpendicular to the path. That way our dot product is simple. So if they're parallel, we get a product. If they're perpendicular, we get 0. And what we're going to do is, because we have a path instead of a surface, we're going to integrate, and you're going to basically pick a spot on your shape, and you just integrate in some direction. And keep in mind, when you have two vectors pointing together, positive. When you have two vectors pointing opposite, negative. So just like we did for Gauss's law, we're going to use something that we already know. We already know what it looks like to have a magnetic field around a current-carrying wire. Take your right hand, right here, thumb comes straight at your face, and your fingertips point in a counterclockwise circle. So I already know that my magnetic field is going to look like this in red. I already know that. So I ask myself, what shape, what type of shape would be useful to have, what's going to give me what I need? Constant B, constant angular relationship, etc. So in looking at this, having a circle. I have a circular shape for my magnetic field, so having a circular shape for the path makes sense. So I'm going to come right here. I have my Ampere's law. B is a constant. I bring it out. All I have to do is integrate the length. The length of my blue circular path is just going to be 2 pi r. My magnetic field, we already calculated this about 5 minutes ago. I plug that in, and what I find is that it all cancels out, and I'm left with this side of Ampere's law equals this side. Instead of Q divided by epsilon naught, I have I times mu naught. That's going to be the charge that is enclosed inside the path, not the surface, the path that I have chosen. So we see the similarities. If I come down here, I have a blue path that I have selected. Each individual segment does what I need it to do. I know that my magnetic field is going to be going around in this counterclockwise direction, so I've got a couple red arrows. This arrow is big because it's closer to the wire. This one's a bit smaller. This right here, this segment, is going to be perpendicular to the field right there because the field's going to be pointing up. So I get 0 for my dot product there. I get 0 for my dot product for that segment. That's convenient. I have this segment right here, a long segment with B. I have a shorter segment here with B2. I have arrowheads, so as I go through and I integrate, I'm going to get a positive dot product because the arrows point together here. I'm going to get a negative dot product because they point against each other. So I'm going to have 0, 0, positive, negative. And what I find is when I actually do the math, my field uses circumference here and circumference here. It cancels out. Here it cancels out. And what I'm left with is simply a positive and a negative term adding up to 0. This A would represent what percentage of the circumference I have here. So it looks like I've got a quarter of a circle, so there's the length times a quarter. So what is this showing us? You have to have your current enclosed inside the path that you choose. If you don't choose something inside the path, everything cancels out and you get 0. Right? So again, Ampere's law, there's our equation, and we've got our different shapes there. Now, in order to figure out our direction here, we're going to use the right-hand rule. Finger curl is going to be the direction of the path. You choose the path. Your thumb is going to be the direction of positive current. So if you do your right-hand rule, it's going to tell you the direction of positive current. So if you look at the one on the left here, if I choose DL to go in the counterclockwise direction, because I know that B is going to point in the counterclockwise direction, my thumb points out towards me. That's going to be the direction of positive current. If I do that, I get a positive dot product and my current points out. Makes sense. Here, my arrows point against each other. I get a negative answer. Well, do the first right-hand rule. Your finger curl is going clockwise. Your thumb points in, which means in is considered the positive direction for current. Your answer is negative, which means that your current must be coming out. So it's hard to say it without showing it, but that's what we have there. So you've got that first right rule to figure out the direction. So you don't have to guess the direction correctly. If you get a negative, it just means the current is going against your thumb. This right here is the same thing, I believe. Yep, I just have it all kind of combined. So DL has a direction, you decide what it is, and it only affects your answer if it's positive or negative. And we have our first right-hand rule. Any right-hand rule with finger curl is called the first right-hand rule. This first right-hand rule allows us to get the correct direction for our current. So if you're trying to solve for I enclosed, you can get a direction as well. The magnetic field in a solenoid. So here I've got my green wire going around. I got my red magnetic field over here. I want to figure out what is the strength of the magnetic field inside my solenoid. So what I'm going to do is I'm going to take a big knife here, slice it in half, and take a side view. This is a cross-sectional view. So I've got my current is coming towards me out of the page at the top. It's going down here. So what I need is a path that will suit my needs. Inside, I have a magnetic field pointing to the right. So I want a segment that is going straight to the right. I'm going to do a right turn, a 90-degree turn. This whole segment is perpendicular to my magnetic field. So I get 0 for my dot product. Out here, I have my magnetic field coming back to the left. It's still perpendicular, 0. The shape I'm going to choose, though, is infinitely long. So when I get all the way out here and I turn, you might say, well, isn't that going with the field? Nope, I made this shape, this path so big that out here, you can kind of see it there, let's do that. I am so far away that the field is actually 0. So I get 0 from my dot product here because I'm so far away. I get perpendicular again, so the only part of my path that has a non-zero dot product is right here. So I come over here, I've got B times L. I already took care of the dot product and all the segments. I've got my mu naught times my enclosed current. Well, if I look, I've got 4, it's the same wire but it's coiled around. I've got 4 currents here. How would I show that? Well, big N is the number of coils. Little n, we call it coil density. So how many coils do I have per meter? So if I take that coil density, multiply it by the length, that is my big N. So that would be my 4 coils perhaps. But what I find here is that the length cancels out and I have my final equation to find the magnetic field inside a solenoid. We call this the Bunny equation. So all that matters is my mu naught value, N, which is going to be the coil density. So I don't need to know how many coils I have. I just need to know how tightly wound it is. 30 coils per meter, 80 coils per meter, whatever. And then the current going through that wire. Because I know the current at each of these is going to be the exact same because it's the same wire. So we use the Bunny equation to find the magnetic field inside a solenoid. All right, same thing there. So a toroid instead is just a solenoid that is bent into a donut shape. So I'm going to end up with a magnetic field inside it going in a circle. So I'm going to, again, if I do my cross-section view, I've got segments of wire out here coming towards me, wrapping around, and then going in here. Since I know my magnetic field is pointing in this clockwise circle, I'm going to make my path a clockwise circle. So when I come down here, a lot of the same stuff comes out. I still get the Bunny equation. So I've got my coil density here, and I've got the length of my path is just going to be the length of my blue path on the right. So I have my length of the blue path. I've got I've got my mu naught, my I, and then my coil density. So I get the Bunny equation for my toroid as well. And this is the last slide. What happens if I'm looking inside a wire? I've got current going through the entire cross section of wire. If we zoom in on this little, on a segment of wire. So we're going to need to use our current density, a concept we talked about last chapter. Actually, it's a few chapters ago now. J, which is going to be my current per area. Even though we call it the density, we use basically our area instead of any volume. So I know that if I have current coming, here it is right here, coming out of the page, if I do my first right-hand rule, thumb comes out, my finger curl shows that I have a counterclockwise direction of red magnetic field. So I'm going to make a tiny little path inside here that is counterclockwise in blue. Total radius R. Little r is going to be the radius of the path that I have chosen. There's my DL direction. So I come over here, I'll have the same field everywhere. Orientation is always going to be a positive dot product, so I go from my integration of a dot product to just BL. The current that is going to be enclosed, I can use this right here. So my current divided by the total area right here is going to be equal to the enclosed amount of current divided by the area of my small blue path. And I get something very similar to my enclosed charge ratio that we've done in the past. And so as I scroll down just a smidge here, I end up with B, the length of my blue surface, which has R as its radius, mu naught times the current enclosed. This ratio shows me the current that is enclosed. And so I have R canceling R. There is my equation. What happens when I get to R is big R? I now end up with this, and I now have a current carrying wire. We already have an equation for that. If I wanted to graph this, I see it right here. This is the only variable R, so I get a nice direct relationship until I leave the wire, and then the wire drops off at 1 over R. So that's everything for the magnetic fields. Now if we continue going forward, which we will do next week, we start to get into electromagnetic induction. This is the fun, mind-bending stuff and all the possibilities, whether it's magnetic braking or whether it's your electric car or charging up your phone with a wireless connection. All those things are a lot of fun to look at, so we'll start getting into that next week. So this concludes magnetic fields. You have online number 24, magnetic fields, and everything you're going to need to know for that goes up until this slide right here, and this is slide number 41. So we did slide 26 through 41 from the posted notes. So bring your questions to Zoom, send me a remind. Seniors and juniors and sophomores, I should say, you all have the same deadline, and that's going to be sometime in June. So don't worry about May 15th being a deadline for you seniors. Okay, so hopefully I'll see you at the Zoom soon.